Hi everyone, I'm Yigong from Johns Hopkins University. Today I will present our work, Pushing Performance Isolation Boundary into Application with pBox. This is a joint work with my co-authors Gongqi and Huang. Providing performance isolation is crucial in multi-application environments to ensure that each application can maintain a consistent and predictable performance. Inter-application performance interference, which comes from contention for shared system resource, has the potential to introduce unpredictable performance regression. To address this issue, decades of work have focused on ensuring that applications running on the same system can coexist without significantly degrading each other's performance. However, modern applications are becoming increasingly concurrent, running a diverse mix of activities simultaneously. This concurrency introduces a new challenge, performance interference within applications, which we refer to as intra-application performance interference. When a noisy task manipulates a shared application resource, such as a global queue, it disrupts the performance of other tasks, causing an overall performance degradation. Here is an example of intra-application interference caused by undue log contention in MySQL. In this experiment, we began by running a client that continuously sends write requests to the servers. After 30 seconds, we introduce a new client executing long read transactions on the same table. To maintain multiple versions of the table, MySQL accumulates an increasing undue log. When a read transaction completes, it triggers the purge thread to clean up the old undue log entry. This cleanup process, while not due to any inherent design flaw in the undue log itself, creates resource contention within the undue log. This contention, in turn, leads to performance interference on the write query. Because of this subtle effect, addressing intra-application performance interference often requires a comprehensive redesign of the contended resource. This can be a time-consuming process for developers, leading to a prolonged period where intra-application interference remains within an application. For example, the parameter InnoDB thread concurrency in MySQL and MariaDB has been reported by numerous users over the past 15 years, until it was eventually deprecated by MariaDB. Given that intra-application interference can exist within application for a very long time, there is a need for system mechanisms to mitigate intra-application performance interference at runtime. Currently, most performance isolation mechanisms are partitioning system resources and dynamically adjusting these partitions. However, these mechanisms are inefficient in dealing with intra-application performance interference because the application's virtual resources remain hidden from the system's view. Consequently, traditional partition methods cannot detect contentions within these virtual resources. Furthermore, the implementation of virtual resources can vary significantly. Blindly adjusting hardware resources may exacerbate the interference rather than mitigating it. An alternative approach is to allocate fine-grained resource quotas to individual application tasks. In this method, the system actively monitors the resource usage of these tasks and blocks any usage that exceeds predefined threshold. However, the application virtual resource usage pattern is consistently shifting. This consistent fluctuation makes static resource quota hard to efficiently maintain a good performance. In summary, existing inter-application performance isolation mechanisms have three limitations. First of all, the current method is difficult to enforce isolation within applications. Second, many application-level virtual resources are invisible to these mechanisms, making it difficult to mitigating interference solely by adjusting hardware resource. Finally, it is inefficient and inflexible to enforce fixed resource quota in addressing intra-application interference. To address these issues, we propose and implement a new OS abstraction called pBox that shifts the performance boundary directly into application itself. With the pBox abstraction, developers gain the flexibility to define arbitrary performance isolation boundary within their application. The pBox provides a set of APIs for monitoring application resource usage and has a new mechanisms to detect and mitigate intra-application performance interference without breaking application logic. Most of the intra-application interference are caused by contentions among the application resource, which are invisible to traditional system resource management. This inherent invisibility makes system resource management difficult to detect and mitigate the interference by simply adjusting hardware resource. Our key insight with pBox is that by making the operating system aware of virtual resource contentions within application, we empower the system to actively monitor and control the resource usage of application virtual resource, thus make effective mitigation of interference possible. Built on this insight, pBox divides an application's execution into independent activities. It traces crucial application resource usage through its library and communicates this information to a kernel-level manager. This manager monitors all pBox resource usage and uses detection algorithms to identify any potential intra-application interference within pBox. When the manager detects such a potential interference, it then carefully takes actions to mitigate the interference. We provide pBox as a set of APIs. With pBox, developers can easily create a pBox, define the isolation boundaries for their applications, activate it, and trace the application resource usage. This API empowers developers to directly build a new isolation boundary within their applications, and pBox can enforce the required performance isolation automatically. Here is an example of using pBox to define a performance isolation boundaries for MySQL user connections. When MySQL receives a user connection, it invokes add connection function. Within this function, there exists a loop that efficiently manages and handles the request sent by the users. Developers can insert and create pBox before the loop to create a pBox and release the pBox when the connection is closed. This API includes a parameter known as isolation rules, enabling developers to specify the desired level of isolations to be enforced on the given pBox. When a connection is in the process of handling a request, the system calls the dispatch command function to carry out the actual task required by the request. Developers can activate the corresponding pBox as needed. This activation can occur before the dispatch command function is invoked. Additionally, developers can write custom code to selectively filter out requests on which they do not wish to enforce performance isolations. To support the event-driven mode where many application tasks share a common thread pool, pBox also provides two APIs for dynamically bounding and unbounding of the pBox to the current thread. With the pBox abstraction, the next challenge is tracing the application resource usage. The most straightforward way is to notify the system with every change in application resources, but this approach can introduce significant overhead. Moreover, application resource design tend to be highly specific. We observe that regardless of diverse implementation of application resource, addressing performance interference typically revolves two questions: identifying the source of delay and identify the tasks that are deferred. Based on this observation, we introduce a new concept called state event that enable efficient tracing of both noisy and victim tasks within the application resource. The state event has four states: prepare, entering, hold, and unhold. Prepare and entering events are designed to capture how long a pBox is blocked by application resource. The hold and unhold events are triggered when the application resource is held or released by the pBox. These events are communicated to the pBox manager through the update pBox function call. Here is an example of using state event to trace deferring time and pinpoint the cause of deferral. When the noisy pBox holds a shared resource, A hold event is transmitted to the pBox manager. The pBox manager in response marks the purple pBox as the holder of this resource. Subsequently, when the orange pBox is blocked by the resource, a prepare event is generated. At this point, the pBox manager begins to calculate the deferring time, which continues until the purple pBox issues an on-hold event, followed by the orange pBox transmitting an in-entering event. The pBox traces all these events across an application, enabling the detection of intra-application performance interference. While state events allow us to determine if a task is deferred by a resource, this information alone is insufficient for detecting intra-application performance interference. Resource-level deferral is a low-level detail that is not equivalent to end-to-end application performance. To effectively detect intra-application performance interference, we require a method to bridge the gap between this low-level resource usage information and the high-end end-to-end performance. To bridge this gap, we introduce a new metric known as interference level. We began by aggregating all the defer times associated with each resource to calculate the total defer time for a task. Subsequently, we compute the interference level by dividing the interference time by the ideal execution time, assuming no deferring time. When pBox executed its detection algorithms, it adopts a worst-case analysis approach. If the current interference level is larger than the defined isolation goal, pBox initiates necessary actions to address and mitigate the interference. Let's dive into the process of detecting intra-application performance interference. Within pBox, we maintain two maps, the competitor map and the holder map. Each of these maps maintains a list of resources. When a pBox sends a hold event, it gets appended to the associated resource list in the holder map. If a pBox sends a prepare event, it is placed to the competitor map. Now, when a pBox is in the holder map release the resource, the pBox manager steps in and checks whether any pBox in the associated competitor map exceeds their isolation rules. If the threshold is exceeded, the manager marks the pBox in the holder map as the noisy pBox and the pBox in the competitor map as the victim pBox. Once the pBox manager detects an interference, it starts to mitigate it. In the mitigation process, it is crucial to ensure that any actions taken do not disrupt the application logic or introducing dangerous side effects. Thus, pBox uses a straightforward yet safe actions. It introduces a delay to the noisy activity. Before applying this delay, pBox waits until all the resources held by the pBox are released to prevent exacerbating the interference. The duration of the penalty in pBox is critical, as it affects its effectiveness. We designed two adaptive penalty length policies. The score-based policies assesses the pBox impacts by comparing if the previous penalty improves the performance or not, and adjusts the length of the next penalty. We also have another policy detailed in the paper. As pBox operates as a runtime abstraction, its performance is a critical consideration. To minimize overhead, we make several optimizations, such as optimizing data structures, pre-allocating important data structures, reducing the number of syscalls, and implementing lazy unbound for bound API. In our evaluation, we want to answer three questions. Can pBox reduce intra-application interference? How does pBox compile with the state-of-art solutions, and what is the overhead of pBox? The pBox is implemented in Linux kernel with a user-level library. We also implement a static analyzer to help inserting the state event. The pBox is evaluated on 5 popular systems. Each one has hundreds of thousands lines of code, and as you can see, we only add less than 200 lines of code for each system, which is a very small amount of manual effort. The last column shows the number of functions we inspect for each application if we insert the code manually. This number can be greatly reduced by our static analysis. We start with micro-benchmark. We test all 6 pBox APIs and compile the pBox create latency with the pthread create. We show that pBox creation is 3 times faster than the thread creation, and the latency for the REST APIs is close to the getPID syscall, which is very lightweighted. We then test pBox on real-world applications. We collect 16 real-world intra-application performance interference cases. The contending results for each cases comes from various categories such as thread pool, table log, undo log, and index search tree. We define a matrix called reduction rate to quantify the number of reduction for intra-application interference. The closer the ratio is to 100%, the more interference it mitigates. If the ratio is negative, it means the policy makes the performance worse. As you can see, the pBox can mitigate the performance interference for 15 cases with an average reduction ratio of 86%. We also conduct a comparative analysis of pBox with state-of-art solutions. These works are designed to achieve performance isolation across applications. The results show that inter-application isolation mechanisms often result in performance degradations in most intra-application performance interference cases, while pBox can improve the performance for most cases. Also, the pBox average reduction ratio is higher than other approaches. In our overhead experiment, we conduct both read-intensive and write-intensive workloads on 5 different systems, varying the number of clients. The results demonstrate that pBox introducing a negligible overhead with an impact of less than 6% in all cases. In conclusion, we found that performance interference can also happen inside applications and is difficult to mitigate. To mitigate the intra-application performance interference, we propose pBox, an abstraction that pushes performance isolation boundary into application by making the OS aware of application resource usage. Our experiment demonstrates pBox successfully mitigating 15 out of 16 cases with an average reduction ratio of 86%. And that's all. Thank you.
Let's thank the speaker. And then I'm going to ask the senior author to join me on stage. Maybe I think you can take the mic. Yeah, okay. Oh, okay. Oh, you're online. Okay, good. So, hi, Bo.
Yeah. Okay, hi, Bu Chen from Shanghai Jiao Tong University. Very nice talk. So, in terms of performance isolation, so I'm wondering what kind of granularity you're supporting, like per request level, or client level, or thread level, and yeah, if how do you use pBox to support all this kind of isolation granularity?
Okay, yeah, so the pBox is basically support the isolation granularities in the task level inside applications. So it's basically we try to push this performance isolation boundary into the applications to prevent the interference among the tasks in the applications. And so the way we try to support like this level of isolation is that we basically give 2 APIs to the developers to specify the isolation areas. So normally developers would specify an area, like a group of activities as an isolation domain that can be like performance isolated from other domains. Yes.
Okay, thank you.
Hi, this is Ming Li from Shanghai Jiao Tong University. Very nice work. So let's suppose 2 pBoxes and 2 resources, like pBox 1 with for pBox 2 on resource A, and pBox 2 with for pBox 1 on resource B. So, so both are victims and noisy. How can your system resolve that? Like the deadlock situation.
I see. So you mean like there's not really a very noisy activities, but both activities are like kind of noisy and
right.
Victims, right? So in this case, pBox for deadlock scenarios, pBox actually cannot solve it. The goal of pBox is not to solve the deadlock, but to solve the performance interference. Mostly that if there's a noisy activity manipulates the system results and causing performance delays. But for the scenario you mentioned, that if there are several activities that evenly contending on these results, pBox can still improve the overall performance by give some penalty to some evenly to each task. So basically to slow down each task speed a little bit, so you can reduce the contention levels, and it can still increase the overall performance for the application.
Well, I'm kind of curious about the isolation level. Will that be something like the priority or not? Because I don't mean the deadlock situation, but they have circular dependency, which causes them, because two resources and two pBoxes, they have circular dependency, and you're trying to solve the circle dependency.
Oh, I see. So you mean, what if some pBox have some resource dependency with other pBox, right?
Yeah.
So this is related to the timing we basically give the penalties. So we will, in order to avoid this kind of dependency, we will actually wait for the noisy pBox to release all the results. Then we can give them a penalty length. So at this time, so since this noisy pBox doesn't hold actually any critical system results, so applying penalty wouldn't cause the dependency issue.
Okay, thank you.
And one more question.
Petros Magnetis, Google. I wonder if at a higher level you have a good criterion of when it makes sense to reorganize or redesign your application to not have these internal intra-application resource conflict versus using an enforcement mechanism like pBox, which is very careful, but of course has some penalty, some overhead. When does it make sense to just reorganize the application?
Okay. So reorganizing, you mean basically redesign the application resource management?
Yes.
Yeah. So the things that for most performance interference cases we studied, the developers already make many optimization to their data structures. But the performance issue can still happen because actually for most performance interference, it requires subtle triggering conditions, and those things cannot be easily tested by developers in the testing phase. And also for some corner cases, it's not easy to actually just writing static code to cover all the kind of workload. So there's still a possibility that performance interference can happen runtime. So I think besides optimize, so this performance isolation is kind of a supplementary tools to optimizing. So if the developers can optimizing tool, it's good. But if there's still performance interference happens in the real-world systems, then running this pBox can still give them a kind of a performance guarantee to the applications.
Great, thank you.
Thank you. Now I'm going to ask you to just stay in your seats for just a few minutes. We should thank the speaker one more time. And